Okay, good morning, CGD. So, welcome to today's seminar. We are joined by Alex Huth, a physical scientist at NOAA's Geophysical Fluid Dynamics Laboratory. So, Alex will be presenting on the role of the ocean in breaking up tabular icebergs. Alex specializes in modeling of ice sheets and icebergs, holds a PhD in Earth and Space Sciences from University of Washington and a BA in Science of Earth Systems, as well as a minor in music from Cornell University. Before joining GFDL as a physical scientist, Alex was a postdoctoral researcher at Princeton University. He was recently awarded an NSF grant in the Office of Polar Programs, which is aimed at developing a tabular calving parameterization for inclusion of climate models. Consequences of having higher fidelity representation of those processes in our climate models are improved understanding of ice mass budget, ice sheet evolution, and higher skill in our projections of sea level rise. So I'll hand it off to Alex here in a moment, but just as a reminder, we will take questions at the end of Alex's talk, where we will not only have questions from our in-person audience, but also if you're joining us via YouTube, you can ask questions on our Slido page. So you can either click the link that is under the YouTube description of the CGD seminars, or you can go to slido.com and enter CGD seminar into the Finder. So at that, I will hand it off to Alex. Thank you.
All right, thank you very much for the introduction, and thank you for having me here. It's my first time at NCAR. It's quite nice. I look forward to meeting a lot of you over the next couple of days. Today, I'm going to be talking about the last 2 or 3 years of work that I've been doing at GFDL, where I've been working with Alistair Adcroft and Olga Sergenko, working on developing methods to represent large tabular icebergs and their breakup within Earth system models where they currently aren't represented at all. Specifically, we're going to be talking about edge wasting and footloose breakup today, which describes the calving of small bergs off of the side of a larger berg due to ocean erosion, as well as breakup due to so-called rift calving, which would be the large-scale breakup of large icebergs into smaller fragments that are still large tabular icebergs themselves. And I will discuss how this breakup affects where the large icebergs drift and deposit their meltwater into the ocean. And finally, I'll discuss what caused the December 2020 breakup of iceberg A68, shown in the upper right here, which I will simulate with our new methods. Icebergs are important because they can influence climate in a few different ways. They comprise about half of the freshwater flux from the ice sheets to the ocean in the current climate, and then they spread this meltwater that they have as they drift throughout the Southern Ocean and the North Atlantic. The meltwater from icebergs can affect sea ice formation and ocean circulation, which I'll discuss in a bit more detail in a few slides, but it can also affect biological productivity, and this is, for example, occurring in the Southern Hemisphere, where Antarctic icebergs are a source of iron to the iron-limited Southern Ocean. Looking at paleoclimate, the classic case of where icebergs can be involved in large swings in climate would be Heinrich events, where the Laurentide ice sheet broke up several times over the last several glacial periods. And from ice-rafted debris sediment samples, we know that there were lots of icebergs released, and this influx of icebergs is associated with a decrease in the Atlantic meridional overturning circulation and regional cooling. In the Southern Hemisphere, there's also been ice-rafted debris sediments collected that suggest other climate influence of icebergs, such as, for example, the icebergs may have drifted farther north during the start of many of the last glacial periods, and this could have reorganized ocean circulation, causing an increased drawdown of CO2 from the atmosphere and facilitating the full formation of glacial conditions. Icebergs also influence climate by increasing albedo at lower latitudes, and giant icebergs, which are found from Antarctica, can obstruct or distort ocean flow. So these big icebergs are the main focus of today's talk. They can be as large as 11,000 square kilometers, is the largest on record, which is about the area of Jamaica, or twice the size of Delaware, and a few hundred meters thick. So this is big enough to distort flow of the ocean. And finally, calving of icebergs from ice shelves can affect the ice shelf flow, and this animation just shows the repeated calving that Pine Island Glacier has had over the past decade or so, which has caused the ice front to retreat and decreasing the ability of this ice shelf to buttress grounded ice upstream. In this case, primarily because the ice shelf has less contact with its lateral margins due to this calving. And with less buttressing, the grounded ice flow upstream could flow faster into the ocean, causing sea level rise. Other reasons to study icebergs, specifically at NOAA, which is in the Department of Commerce, focus on more economic reasons. So iceberg risk is a big one. The International Ice Patrol was founded over 100 years ago when the Titanic sank, and their role is to run aerial surveys and do some modeling to prepare these sort of iceberg maps that let ships know where icebergs are, as well as fixed platforms such as oil rigs and submarine pipelines and cables. And in the Southern Ocean, the National Ice Center tracks giant icebergs. And the International Ice Patrol is run out of a NOAA facility in Maryland, but is run by the Coast Guard, actually. And then there's been a variety of crazy ideas of using icebergs as a source of fresh water, that is towing Southern Hemisphere icebergs up to arid desert regions and extracting the fresh water. And every couple of years since the 70s, somebody devises a new way to be able to do this that gets a little bit of press, but it's a challenge because icebergs tend to break up and melt as you bring them to warm water. And then once you get them into a harbor somewhere, they're just going to melt really rapidly and cause some sort of ecological disaster. And I don't know. But at GFDL, icebergs have been part of our models since 2010. And how it's treated is fresh frozen runoff from the land. Well, we have snow that falls on the ice sheets, and then it's routed to the ocean through a river network for lack of an ice sheet model, although the ice sheet model is coming. And so this frozen freshwater runoff before 2010 was originally just melted immediately at the coastline where it was discharged. But once we added icebergs, then it is instead treated with the iceberg model, and the icebergs drift, and they can drift for hundreds to thousands of kilometers, and they melt along the way. And now the meltwater is distributed farther away from the coasts, as shown in these two plots. The iceberg model at GFDL, the one that is used in global climate simulations at least, is a Lagrangian point particle model, where this frozen freshwater runoff at the coast is converted into icebergs that are treated as if they have different sizes. So there's different size categories. Each iceberg has a length, a width, and a thickness. So it has a cuboid geometry. And then that geometry will change over time as the iceberg melts and erodes away. The key decay mechanism in this regard is wave erosion on the sides of the iceberg. And then there's basomelting from turbulent heat flux, and also melting along the sides due to heat fluxes from buoyant convection. And the icebergs drift according to a force balance described by the plot on the top, where you have a pressure gradient force according to the sea surface slope, Coriolis force, a rather unimportant wave radiation force, which is an empirical parameterization, and then three drag terms: sea ice, ocean, and wind drag, which has coefficients. It's a quadratic drag law that is tuned to observations as well. So while these icebergs have this cuboid geometry for the treatment of drift and melting, on the ocean grid, they're treated as non-interacting levitating point particles. What this means is the icebergs don't interact with each other, they don't run into each other and bounce off. And by levitating, I mean they don't impart pressure on the ocean's surface. So the ocean really just cares about the heat flux to and from the icebergs and the meltwater. The plot on the far right here shows the sea ice anomaly, sea ice concentration anomaly, when adding icebergs to the model versus just depositing the meltwater at the coast. And you can see that there is an increased concentration of sea ice when you add icebergs in East Antarctica and the Weddell Sea sector, and decrease in West Antarctica. And the reason this happens is because in this particular simulation, the majority of the iceberg mass is carried by the larger icebergs in the simulation, which tend to travel along with the Antarctic coastal current to the west, and therefore are transporting a lot of this fresh water contained in the icebergs over to the East Antarctic sectors, and eventually the icebergs escape out into the Antarctic circumpolar current, primarily through the Weddell Sea. But wherever there is additional fresh water added to the ocean from icebergs, we tend to get more sea ice, assuming that we are at a high enough latitude that sea ice would form. And we can look at the ocean hydrography. These three plots just show the density anomalies when adding icebergs in the three different sectors, so the West Antarctic sector, East Antarctica, and the Weddell Sea. And when you have this additional iceberg meltwater flux, what you get is stratification of the ocean column with fresher, colder water by the surface, which is favorable for the formation of sea ice. It's also colder, not just because the meltwater is cold, but because the ocean loses heat when it melts the icebergs, and consequently, you get more sea ice forming. So that's one way that the icebergs affect ocean and sea ice. Iceberg size is an important parameter that dictates where the icebergs drift. Larger icebergs will survive farther out into the ocean. And what the plot on the left shows here is that on the x-axis we have a variety of different iceberg areas, and what it shows is this black column here shows that the largest icebergs that are between 1,000 and 10,000 square kilometers in area represent the vast majority of the total surface area of all bergs, and the red column shows that they represent a tiny fraction of the total berg count. So not very many large bergs, but they represent the most surface area and mass of all icebergs. In fact, icebergs with area greater than 100 square kilometers represent 90% of Antarctic iceberg volume. And the opposite is true of the small icebergs. You get a ton of small icebergs that represent a very small amount of the surface area of all icebergs. And so when we look at observations, this is plotting large giant icebergs between 5 and 11,000 square kilometers from the National Ice Center's observed data set from satellite observations. And this ends up kind of matching what we get when we implement our GFDL model, but the difference is that in this plot for our GFDL model, this is plotting the largest 4 iceberg mass classes that we have, but they're actually much, much smaller icebergs. So we're only modeling icebergs up to 3.5 square kilometers, which is several orders of magnitude smaller than what's actually observed. And the reason that we do this is that if we model larger icebergs, so here just up to 1,000 square kilometers, which again is still an order of magnitude smaller than the largest observed, they travel far too north to lower latitudes. And even though we're getting the distribution of these icebergs fairly similar to observations, the large icebergs and small icebergs are going to decay at different rates, and therefore the meltwater might be in different places. So the goal here is to be able to represent these large tabular icebergs without them traveling so far north. And the key there is that we need a representation of iceberg breakup, which is currently lacking, and that will help these icebergs decay faster and not travel so far to lower latitudes. So there's 3 styles of iceberg breakup that are commonly considered. The first being rift calving, which as I mentioned on the title slide is the breakup of a large berg into still quite large but smaller pieces. Then there's the edge wasting of the footloose mechanism, which I'll describe in detail, but essentially we get erosion along the sides of a large iceberg that allows it to decrease in size but keep its same general shape. And then finally, rapid disintegration of icebergs can occur when a large iceberg finds itself at a low enough latitude that melt ponds will form and cause the berg to hydrofracture catastrophically. I will mostly talk about rift calving and the edge wasting or footloose mechanism today. And I'm going to split the rest of the talk into 2 separate studies. So the first study is to represent these larger bergs and their breakup within the existing point particle iceberg model that we're using, and then test what the effect of these larger icebergs with breakup are going to have on the spatial distribution of the icebergs and the meltwater. The second study is going to be a reformulation of the iceberg model with a variety of advantages that will allow us to capture rift calving more accurately, for example, in the true shape and size of icebergs. But the reason that I'm presenting both of these results is that this current study, with just implementing the point particle model that the existing point particle that we have now, this is really what's going to be representing the current state of iceberg modeling at GFDL and in climate models for the next few years until the next generation model that I'll describe in the second half is ready for general implementation. So if you're going to implement an iceberg model in a climate model, this first study is probably the way that I would recommend doing it for the time being. The way the footloose mechanism works is you get wave erosion at the water line that creates a notch in the iceberg side, and then the freeboard above that notch of the iceberg calves off, and you're left with this underwater foot. The foot experiences a buoyancy force that causes the iceberg to flex like this, and you have this characteristic rampart and moat shape. And with this bending comes internal iceberg stresses that can cause a fracture to form roughly a bit more than an ice thickness to the interior of the iceberg, and this fracture propagates the full thickness of the iceberg to calve off a so-called childberg from the parentberg. And at the right, this is just an example of an observed iceberg with a foot that has grown underwater. So to parameterize the footloose mechanism in our point particle iceberg model, we look to elastic beam theory. And the way this works is with this underwater foot, the buoyancy force, this is essentially treated as a point force at the end of a beam, and from that you can solve for the deflection and internal stresses of the beam to determine where the highest stress is that would cause fracture to determine the length of the childberg that calves off. And these equations mean very little without full derivation of how this model works, but I'm just putting them up there to demonstrate that this model is quite simple. What we're actually solving for is the length of the foot needed to cause a childberg to calve, and then the length of the resulting childberg in this 1D horizontal dimension model. There are a couple of parameters that control how this model behaves that aren't that well defined for ice. These are material properties, including the yield stress of ice, that is the stress under which the ice will break, and the Young's modulus or elastic stiffness. And the way that this controls this model is that with greater yield stress or a less stiff berg, you need a larger ice foot to cause a childberg to calve off, and you'll get a larger childberg when you have a stiffer parentberg. All that being said, what's going to happen later is I'm going to do a parametric study where I vary these parameters, and from these parameters you can sort of derive what a characteristic footloose decay rate is versus other simulations and the length of childbergs, and I'll be able to look at those and explain how that influences the way that the footloose mechanism can change the distribution of icebergs and their effect on meltwater distribution. To implement this in our point particle model, now we need to consider two horizontal dimensions. So instead of just tracking the length of a foot, we're actually going to track the area. We already have a parameterization for the freeboard erosion that I mentioned earlier. This is more or less proportional to the sea state. And then you subtract out the melt from the sides, and that leaves you with the area of the foot. And if we assume that a childberg has a width that is 3 times its calving length here, and that means it has a 1:3 ratio in its horizontal dimensions, which is often observed, then we simply calve a childberg whenever the area of the foot exceeds the length of the foot times 3 times the length of the childberg. And then we reduce the parent length and width evenly to account for the fact that the footloose mechanism generally shrinks the berg from all sides without changing its overall shape. Now, the footloose mechanism alone is not going to be sufficient to prevent large bergs from traveling too far north. So we need to have some implementation of rift calving. We can't model it explicitly in part 1 of this talk in this point particle model. So what we do is we simply set the max Antarctic iceberg area to 1,000 square kilometers, which is smaller than the largest bergs recorded, which here's the top 10, range from 5 to 11,000 square kilometers. But this is consistent with the assumption that the large bergs rift calve into smaller pieces quickly after calving, which is an okay approximation in some ways. So here's the red particles here is B15, which broke up immediately upon calving, and then the particles all take their own path. But there's no guarantee that all of those small particles are actually less than 1,000 square kilometers. And oftentimes, as we see with A68 here, here, the bergs maintain a much larger area than 11,000, 10, they keep a larger area than 1,000 square kilometers over most of their life. So it's not a perfect parameterization, but it is necessary at this point. Note that another advantage of doing this is that we're not going to be representing bergs that are larger than a grid cell, which is not ideal for the point particle model. These larger bergs overlapping multiple grid cells should have ocean velocities and other external forces that vary along their body. And I'll present a solution to that in the second half of the talk, but that is just to say that this is a limitation of the current study, is that we're only having bergs that are 1,000 square kilometers in area at most. That being said, it's still increasing the max iceberg area by several orders of magnitude. So if we plot the old iceberg size distribution versus the new on the left, old on the right, with the same total mass, you see that on the right we have a ton of icebergs, with the largest one being 3.5 square kilometers. On the left, the largest is 1,000 square kilometers, and there are fewer bergs. And in part because of this and other improvements, we actually end up speeding up the iceberg model. So that runs about twice as fast, which the rest of the climate modelers like, because nobody likes a slow iceberg model. So here's the parametric study, where we're going to vary the ice stiffness and the yield stress between experiments, implementing the footloose mechanism or not, with the large iceberg size distribution up to 1,000 square kilometers. So what this is a 60-year run after a spin-up period where we have, this is an OM 4.5, so this is a half-degree model with a dynamic ocean and sea ice module, so that's MOM6 and sea ice and CIS2 at GFDL. But runoff and atmospheric forcing are prescribed from JRA 55. And so on the bottom right, this is the National Ice Center's observation for the average area of large icebergs, that is icebergs between 200 and 1,000 square kilometers that drift near each grid point. And if we don't have our footloose mechanism, our large bergs, as expected, drift to too far of low latitudes. When we do implement the footloose mechanism, which is the top 3 plots with different material properties, we get a much better match to observations. Note that those simulations with the slowest footloose decay rate have bergs that travel farther north than those with the fastest footloose decay rate. That makes sense. If a berg decays faster, it's not going to survive as long. Now let's look at the average meltwater flux over the simulations. So with the original small GFDL iceberg sizes up to 3.5 square kilometers, this is what the melt flux looks like, averaged over 60 years. And here are the anomalies when we add the footloose mechanism. For reference, here are the iceberg extents and areas from the previous slide for each plot. Note that in this case, despite having the lowest and fastest footloose decay rates in these 2 plots, which will result in the large bergs going farther north or traveling the least far north, they actually have more similar meltwater distributions than this middle plot with, this upper plot, which has a sort of middle of the road between these 2 in its large iceberg extent. And the reason why this happens is while the large iceberg extent sort of determines where the child icebergs are calved, the child icebergs, their dynamics and where they travel depends a lot on their size, so that smaller child bergs will spread more widely from the coast due to katabatic winds. And so with these 2 plots, they have the same small iceberg sizes, and so we get a more diffuse distribution of icebergs throughout the Weddell Sea sector and in the Antarctic circumpolar current, versus the top plot where there are larger small bergs, and those small bergs that are larger in this case are more likely to follow ocean currents, which is what the large parent icebergs do as well. So there's 2 effects going on here. The footloose mechanism describes where the small bergs are deposited and where they calve from the large bergs. It determines how quickly the large bergs decay, and then also the size of these small bergs determines where they end up. In the northern hemisphere, the max iceberg area is under 2 square kilometers because we're calving from small fjords. In this case, the footloose mechanism, it activates and finishes rather quickly. I mean, it pretty much just, once the icebergs enter the open ocean, they just calve to their smallest iceberg size according to the footloose mechanism. So essentially what it's doing in the northern hemisphere is just completely changing the size distribution of the bergs, the large bergs, to turn into the small bergs. And so in that case, the small berg sizes also matter in determining where the large bergs, the overall general iceberg distribution. So with small bergs, they decay more quickly, they travel less far south. So to summarize this study, before I move on to the more interesting second half of the talk, by prioritizing breakup, we increase the calving size distribution by a few orders of magnitude, 2 orders of magnitude, and the model areas and drift trajectories resemble observations within those constraints of being under 1,000 square kilometers in area. And so this is going to be the default for the global climate simulations at GFDL. It does modify the distribution of icebergs and their meltwater compared to our previous model. And it was published last year in James if you want to learn more. Now, we're still neglecting the largest iceberg areas and proper representation of rift calving, which leads me to the second half here, where our goal is to develop a new iceberg component for climate models that can represent the true size and shape of all bergs, so no longer being constrained by being smaller than a grid cell. And this includes rare large bergs that have substantial meltwater, such as A68A shown here, which I'm going to try to simulate its drift and breakup. So iceberg A68A calved from the Larsen C ice shelf in 2017, and then 3 or 4 years later, it broke up near South Georgia Island after maintaining its iceberg area fairly closely within a couple thousand square kilometers. It was originally 5,800 square kilometers, which is about the size of Delaware. And so it got a lot of press at the time for being the largest iceberg in the world, and it had 1 trillion tons of meltwater in total. So having this new iceberg framework where we can represent these large icebergs in their true size is important because these calving events and the breakup of these bergs and their decay, it can kind of act like a volcanic event or something that is fairly rare but can have a big climate impact. So we would like to be able to represent bergs like that rather than having more of a mean field approximation that we get modeling only smaller bergs. And this new model will include breakup due to rift calving. So here's the new model. The improved kinematic iceberg dynamics module, or IKID, captures the true iceberg size and shape because now instead of using point particles, we use particles with finite extents that are bonded together into one big conglomerate that can overlap multiple grid cells, and therefore external forcings can vary across the iceberg body, which is important in getting its drift and rotation correct and allowing contact between bergs, which is now represented. And internal stresses are captured on the elastic bonds that connect the particles, and if these stresses are large enough, these bonds will break to represent rift calving. And we can also capture grounding. So all in all, we can get simulations like the one shown at the right, where we have a large tabular berg that approaches the seamount, hits the seamount, breaks into 2, and then all of those pieces rotate and drift away. So a big problem with bonded particle methods in general is that they're notoriously computationally expensive. And since we want to use this in climate models, we need to address that. The reason that they're so expensive is that they require very small time steps so that the elastic wave between these bonds does not travel further than 1 particle away over a time step. But that's really the only force that needs to be evaluated on such small time steps. So what we do is we implement a multiple time stepping scheme to increase computational efficiency, where we evaluate all the external forces on a long step, which for the A68 simulation that I will show towards the end of the talk will be a half-hour long. And then we have a series of 90 short sub-steps to evaluate the internal forces on these bonds, for example, and that's where position updates and grounding are also performed. So the long step forces are the same external forces as from the previous point particle model. The only difference is that now that we have particles that are bonded together, any forces that are acting on the sides of the berg, such as ocean and wind and sea ice drag, they're going to have to be decreased if a berg has a lot of bonds with its neighbor to account for the fact that only part of the face of the berg is exposed to those external forces. A really interesting part of this parameterization that we have, or this model that we have, is that we actually evaluate contact between iceberg conglomerates on the long step, and this is for reasons of computational efficiency. This contact is modeled as an elastic spring force, so typically it would be done on the short step, but we do it on the long step. And so typically it would be proportional to the overlap between two particles, this elastic spring force. And the reason that we want to do it on the long step is that first of all, it will help with parallelization, which I'll show on the next slide. But second of all, it will reduce the amount of times that we need to find contact pairs between bergs. And so rather than using a stiff spring for this contact, we use a much weaker spring so that we get a stable contact between bergs without causing the model to crash. But this can cause bergs to overlap quite a bit. So to get around this, we simply enforce that instead of the overlap between two bergs being what causes this elastic force, instead we allow contact to happen before the two bergs actually overlap. And in this exaggerated example, you see that the bergs now no longer overlap each other. So a little bit of a hack there, but it helps a lot with parallelization, which is really one of the most expensive parts of the model, is just transferring data between processing elements. And so the way that this scheme works is that when you have one berg conglomerate that overlaps multiple processing elements, so here processing element 3 and 1, we will copy the entirety of that berg conglomerate to both of those processing elements, as well as any bergs that are in contact range, which again we evaluate on the long step. So processing element 3 will evaluate the forces and melting, or well, just the forces, I suppose, of this iceberg conglomerate and any particles within contact range. And processing element 1 will also see the same thing. So sort of redundantly calculating the forces on these particles. And for that reason, the largest iceberg in the simulation will somewhat control some of the computational efficiency in that regard. But nevertheless, we really reduce the number of contact searches, only have to do it once on the long step rather than 90 times on the substeps. And the transfer of data between processing domains only needs to happen once on the long step rather than repeatedly over the substeps when positions are updated. The short step forces include the bonded particle forces within a conglomerate, as well as any contact between bergs that are in the same conglomerate but not bonded that would represent, for example, a rift. And this is just regular stiff spring overlap between two particles for the contact force. And at this point, the model really just reduces down to a parallel bond discrete element method, where there is a normal and shear force between bonded particles, and then two torque terms, one from shear, one from relative rotation. And these torque and shear terms prevent unrealistic bending, which can be seen here. We have a fracture criterion where bergs break when bonds break when the max tensile stress exceeds the tensile strength. You can also have a shear stress criterion, but we just use the tensile stress for our A68 simulation. And we find that grounding works well on the short steps as well, which is a simple linear drag law whenever the keel of the icebergs exceeds the seafloor depth. So here's our test case. We have A68A approaching South Georgia Island, and it rotates and keeps drifting south. It was originally worrisome that maybe this iceberg would crash into South Georgia Island and literally crush penguins, or at least get stuck and grounded there and cut them off from their food supply. But instead, it only nicked the seafloor, causing this first berg to break off of its northern tip, and then it continued to drift south. And this second breakup event, where the thin finger section of the berg broke off, it was very unclear as to what could have caused that, because it happened where the seafloor depth greatly exceeded the depth of the iceberg keel. So we're in the deep open ocean here, could not have collided with the seafloor. So we want to see if we can simulate this exact drift and breakup using our new methods and determine what caused this second breakup event. And our hypothesis here is that this second breakup event occurred when we see here that the finger of the iceberg that broke off was within this stronger ocean current, shown by these yellow arrows, than the rest of the berg, which is in a weak ocean current. And therefore, we hypothesized that, well, maybe there was strong enough change in stress, horizontal stress along the iceberg body to snap it into pieces like a twig. So in other words, the hypothesis is a second rift calving event caused by ocean current shear. And this is a breakup mechanism that hasn't been reported or considered previously, and so we can test it with our model. So take a step back. The goal here, can IKID simulate the observed drift rotation both breakups, and is the second rift calving event caused by ocean current shear? And here's our model results. Indeed, we're able to get the drift and rotation of the berg correct. When it hits the seamount, top calves off, and then the second breakup event indeed occurs due to ocean current shear, because that's really the only force in the model that possibly could cause it. Our ocean current velocity, sea surface heights, vector winds, they're all the data sets that are used for the Oscar data sets to calculate ocean current velocities from satellite observations. And importantly, the tensile bond strength for all of the bonds in the simulation are 18 kilopascals, which is of similar order to what was estimated for large tabular bergs from an observational study under similar modeling assumptions. The computational efficiency, it only took 8 seconds to simulate each day of iceberg evolution, and that's for the multiple time stepping scheme, which is sufficient for climate modeling, and presumably we'll be able to speed this up with some more optimization, and if we use coarser particle resolution, which means we can use larger time steps. So to summarize, ocean current shear may trigger some iceberg breakups, and intuitively, longer bergs are probably more susceptible to this type of breakup because they're more likely to overlap a strong and weak ocean current simultaneously. This new bonded particle iceberg model has the advantage of representing the true iceberg size and shape, no matter how big or small the iceberg is, and it can account for internal and external stressors that vary across its body, and therefore it can capture rotation, rift calving, grounding, and so on, and it's computationally efficient. This was published last year in Science Advances, Ocean Currents Break Up a Tabular Iceberg. And as I noted previously, it's not quite ready just for general use within climate models, for global simulations at least, because it really just needs more tuning. We need to simulate more bergs to make sure that the material properties that we used, that is its stiffness and its breakup parameter, stress threshold, are appropriate. And so in the meantime, we use the point particle plus footloose. In other next steps that we have planned, it's very important that we are able to calve these bonded particle icebergs from ice shelves within our system models, because they are fairly rare events and their calving depends on iceberg stresses, ice shelf stresses. And I have some work along these lines where I'm able to simulate the calving of iceberg A68 from the Larsen C ice shelf using a damage mechanics model. And this requires a fairly high resolution grid, so 0.5 kilometer to 1 kilometer or so. So may not be perfect for global climate simulations, but you could at least learn about tabular calving, which is not very well understood, and maybe be able to parameterize it within these global climate models to capture these rare but important iceberg calving events. Furthermore, there's plans to have the icebergs from the bonded particle icebergs actually displace the ocean surface as well as sea ice, and that's a problem for the oceanographers, where we want to be able to do that on a long time step and without creating artificial tsunamis and so on, which is being worked on. And finally, having the bonded particle method that represents the true size and shape of the icebergs, we should be able to do some coupling with the atmospheric fluxes and therefore also capture things like melt ponds forming and the last mechanism of iceberg breakup that we know of, which would be the hydrofracture for quick disintegration of these large bergs. And with that, I will take any questions, as that is the conclusion of the talk. Thank you for coming and listening.
Okay, Alex, thank you for your talk and also that unique imagery in your descriptions of breaking off and the drift. So let us open it to any questions that we might have. from the audience. And then again, if you are joining us online, you can input any questions into our Slido page. Yeah, Günther?
Thanks, Alex. That was great. When you say that the iceberg model right now is very expensive for climate model, can you give us like a rough estimate? Because
For-
ocean and atmosphere typically are very expensive. So compared to those,
For this model in particular,
yeah,
for the ice shelf stuff.
for IKID and
Oh, for IKID. Well, IKID is okay. That's, we're modeling one of the largest icebergs of all time there, and it was taking 8 seconds to model a day, so that's not too bad. This rifting model here, though, I think is probably too expensive, mostly just because it requires a pretty fine grid resolution. And the ice sheet model that's being developed at GFDL, we're working on the same grid as the ocean, which is a spherical grid. So trying to get down to a half a kilometer is challenging.
Thank you for the interesting talk. I wanted to ask, you may have said this, but what resolution of ocean model do you think you would need, and I'm talking about like a global Earth system model, to replicate that event? Because it looked to me like it was A68. I think, it got caught in an eddy or something like that. So I would presume you at least need somewhat eddy permitting. And also it gets grounded on that seamount, and I don't know, what resolution you would need for bathymetry to be able to reasonably simulate that.
That's a great question. I'm trying to remember what resolution I actually used in this model. I want to say I was at either an eighth or a third of a degree. GFDL is working towards 12th degree models, so that should be okay. We're really just trying to simulate the next couple of, GFDL is in our mission state focused on decadal to centennial climate simulations. So that should be okay. As far as the capturing the bathymetry, the way it works in the models, I have sort of a quadratic interpolation of the seabed depth to the iceberg model. So it can kind of get some subgrid scale effects more than, say, a linear interpolation would.
Okay. Oh, yes. Gustavo.
Can this model be run in a regional configuration?
Yeah, I mean, right now it's running only regionally, but just using assigned data for ocean currents and wind and whatnot. As long as you can come up with a regional configuration for the ocean and atmospheric forcings, then there's no problem.
And a follow-up question. I know you said that embedding the iceberg into the ocean is the oceanographer's problem.
Yeah, I'm a glaciologist, so
Yeah, fair enough.
any questions on the ocean side?
Just out of curiosity, have you guys tried anything? Because in the beginning you showed that picture of getting more or less sea ice depending on the inclusion of with and without icebergs. Presumably when they are embedded, we always hear you just see the tip of the iceberg. So most of the mass will be under the water. Freshwater will be released at depth. You have upwelling, so you might end up carrying more heat into the surface.
Yeah, there are certainly some complex interactions between the iceberg meltwater and what's going on with the ocean column. On Stern, whose results I showed for the sea ice results, actually did a paper on that if you want to check it out, as far as embedding a tabular berg with his bonded particle method, which was sort of the basis for IKID. Yeah, upwelling is part of that for sure. So it probably depends a lot on the local density column already in the ocean and how that interacts with whatever melt you're inputting. Yeah, good point.
Okay. Oh, yes, Stan.
Thanks. For the footloose mechanism, you said that you were using the local sea state to get at the wave climate. Do you think that would there be a benefit from having a full wave model to get remote influences, or is it mostly the local sea state?
Sure. I would say that the challenge in that regard right now is that the erosion parameterization that does exist isn't even all that well understood. So if we can actually have a true wave model, and I think there's a few people that are working on this, improving this erosion parameterization, then yes, that would certainly help. But at this point, even with a wave model, I don't think it's all that well understood. Yeah.
We have a question from Brian.
Have you tried an experiment where you tow an iceberg from the high latitudes to the low latitudes?
I have not. Would be quite interesting though. Yeah.
Okay, do we have any other questions? I'm just going to run around quickly to see if any have come in online. Okay, doesn't look like any online. Any more in-person questions? Oh, yeah, Fred.
Hi, thanks for the talk. Can you give us a better idea maybe of the status of iKits? Because what you're showing now is just like the advection in evolution of the iceberg, but how close are you to have that running into like a climate model with like all the runoff aspect and etc.?
Yeah, I haven't tested it in a fully coupled situation yet.
Okay. Any more questions? If not, we're coming up to the end of the hour, so let us thank our speaker, Alex, again. And I will see everybody back next week for one of our own Andy Wood.